Now that, you know where that's from? I didn't have to do anything there. That's My Fair Lady. It's a Hirschfeld drawing.
Welcome back, everyone. So it's my great pleasure to introduce our final speaker. So in organizing the conference, we had one principle, which is that you have to end on a high note. So we're very excited to have Mark Wilson as the final speaker. And the second thing that was clear to us from the start of organizing this conference is that Mark was the one philosopher that we definitely had to have on the program. So his work, in some sense, there was a trend in 20th century philosophy of science to look at scientific theories with all the tools of predicate logic at hand. And I think Mark has argued in a variety of ways that you should actually look at science with the tools of applied math at hand. And he's, through a variety of his papers and his book, Wandering Significance, shown the fruits of taking a look at science with a proper appreciation of the importance of applied mathematics. So for this conference especially, it's wonderful to have him here, and he'll take it away. He'll tell us about approximations, hidden hands. So thank you very much, Mark.
The first thing is I have to thank the Templeton Foundation for giving me a year's leave, and I have to then thank Bob for actually applying for the grant. I didn't have to write a single line. So anyway, yeah, it's kind of too bad that I couldn't have done this a little bit earlier, because I was talking to Rob about this. One thing that I believe, where particularly numerical analysis can help us in philosophy and kind of nitty-gritty detail and understand how hard it is to get numbers out of formulas. There have been many kind of, I call them necessary tensions in the formulation of physical theory, and I'm going to talk about classical mechanics, that were sort of necessary. There had to be, well, I'll give you an example in a minute, had to do some kind of weird things to get the whole enterprise up and running. Right. These in turn, historically, I won't have time to talk about too much, had enormous impact on issues in philosophy. So Leibniz wrote the first differential equation for a loaded beam, right? And it led to, it's pretty directly connected with some of his wild philosophy. Kant was influenced, I think, by similar issues and so forth. And in philosophy, we've become so abstract that we lose track of this. And so the people who are more aware of how hard it is with those little threads can help us better understand some rather grand issues in how humans should work with concepts over time. Because that's what I'm going to try to talk. And the example I'm going to pick, when you learn elementary physics, you're asked to swallow some things that I remember I thought were pretty strange, and that's partially because I was educated with too much logic. and so this isn't alone for me. This is from a well-known book on nonlinear elasticity. Most modern expositions of basic mechanics, in a freshman book, ask the reader to emulate the Red Queen by believing 6 impossible things before breakfast. Okay, well, I could probably figure out 6, but here are 3. I'm just going to talk about the setup of the string equation. In fact, not even the wave equation, though historically that's what came first, but just a loaded, an equilibrium position of a loaded string. Okay, and if you look, there are lots of different varieties, but you'll find a mixture of these flavors that, though it's supposed to be a completely flexible string, when you get real small and you look at the so-called free body diagram, all of a sudden it's okay to treat it as rigid. In fact, that's actually a postulate in Kelvin and Thomson and Tate and so forth. Then there's the assumption that when you stretch it, it moves in a vertical direction, right? It doesn't, of course, that would mean you couldn't have sound waves go through it in the x direction, okay? And then the thing, you're acting like when you look at your free body thing, you're taking its boundary and doing something to it, right? But when you take the limit, those boundary events, which have to be different than the interior events, somehow disappear. those are things that troubled me as a kid. Okay. Now, one thing that we're taught in philosophy is that many important computations are mere approximation, and they don't play any central role in establishing this, I put in quotes, the semantic contents. That means the meaning or the information-bearing contents of your theory. And later on the talk, I'll talk about some very dominant movements within philosophy of science that disdain any attempt or even have any concern with how you get numbers out of the theory. Okay. So and I think that this is why it's a general philosophical theme. This comes from misunderstanding some very fundamental things about how language works, how it encodes information. And a lot of it's contextual. I'm not going to develop that too much here. And I also want to stress these are necessary tensions or ways of conveying information, because if we hadn't tolerated these things, we could have never developed classical mechanics. Because we'll see. And in particular, I'm going to tell you a story, and it took until the 1960s before I think people got a clear view of this, and it took the functional analysis to figure it out, that one thing that kept classical mechanics modeling on a productive track. And if you look at Thomson and Tate, those great masterpieces of the late 19th century, they've got all the fundamental important classical models up and running. What steered them to good ends? And there are, and the basic thesis I'm going to give, there was some secret peeking at the approximations, right? And they didn't realize that they were doing that, and I want to give you a story about how that happened. Okay, and here's sort of a, I don't know if this is how, this dates me, but this is a famous comic book from the 50s. Okay, but you know these things, whether it's Donald Duck or The Simpsons, you know, there's always some head of a family, it's always a male, right, that believes that he does everything. But he's always screwing up, and there are a whole bunch of little helpers, nephews or Simpsons children, running around fixing up dad's screw-ups. Okay. Well, that's how how we're going to look at basic formulas in mechanics as kind of fake dads that pretend to do more about carrying content than they really can manage. And we want to look, so the thing is, it's things that are actually approximations, finite elements, we'll see, are doing that sort of clean up for dad sort of activity. Okay, and this is I guess just stating that again, I adapted this from the typical English worship of Newton diagram, but I put a single formula here, actually the formula for a loaded string, a real simple equation. And it's, the analogy to my Donald Duck thing is, we think, and most philosophers think, and this is part of philosophy of language too, that all the meaning, all the true descriptive content is carried completely by that formula, and not by the family of approximations that may live in the neighborhood, right? And I'll call that individual sentence worship. Okay, so we're going to get a better picture. Okay, so I'm going to particularly concentrate at the beginning on so-called fundamental solutions, which go back to the very beginning of the string equation, because it occurs in a famous debate between D'Alembert and Euler about situations like this. Suppose that we have a string loaded by just a single unit weight, right? Shouldn't just that V shape be the natural equilibrium condition for that string? It seems intuitive, right? But D'Alembert, he complained to Euler said that, and but D'Alembert said, well, but my equation, when I derive it, you take the tangents, and when you squeeze in, you get a curvature, right? And so it's the curvature in the string gives a strain energy that balances the potential energy. They didn't talk about in terms of potential energy, but that balances the gravitational term. Okay? And those are called fundamental solutions, but they were usually called, they were set off to the side. And I'll call them pseudo-solutions because they don't satisfy the normal notion of what a solution should be. Because this equation demands a curvature, and they certainly don't have that. Okay. And so, I just said this, so they were traditionally tolerated as useful approximations, but they had no bearing on what the equation itself meant. Right. And I quote the Wizard of Oz here, I don't know. Even in philosophy of science, this is just the norm today. Approximation, that's why you guys get dismissed. You know, is irrelevant. You know, pay no attention to those guys behind the curtain or those approximations. Okay, that's what I want. Okay, but unacknowledged labor demands its rights. Okay, so let's go back to that. Now, there's always been stories or justifications about what these fundamental solutions, you know, represented. And there's a whole class of different ones. In some sense, I'm just picking a very simple example here. But there's, well, they only live as inside integrals, or they're allowed to live on boundaries, and so forth. But they used them. And this is the fundamental solution, right, is the doorway through which you get almost all your results in linear differential equations. Okay. But the problem is, and this goes back to what D'Alembert expressed, what D'Alembert was worried about in modern terms, is that we can understand that the string maintains a shape or counteracts gravitation by having a strain energy. But it's stored normally in its curvature. Okay? And so the question is, how can we make sense of strain energy for a string that doesn't have any curvature? There's a sharp corner thing. Okay, and the answer, this became a very serious, well, I'll even give you sort of the context right now. In the calculus of variations, and this is where Hilbert suggested a basic answer. So, and this, by the way, often philosophy textbooks talk about the crisis in analysis in the 19th century as being about the definition of a derivative or something that needed Cauchy, Weierstrass. But it was problems like this that go very deep in mathematics. They're connected with a lot of Riemann's work, which became problematic because of these kinds of issues. But the calculus of variations was one of them. So our problem is, if we have a river and if you have enough assumptions about how the currents work, and you're trying to go from a spot on the right and get to that island, but there's an obstruction, right? It can be that the optimal rowing path in terms of energy effort is a bang-bang thing where you go completely straight to the other bank, you know, and then turn, right? And if you take any other path there that was be curved, then you have more rowing effort because you're trying to turn your boat in the middle of the stream. Okay, so we want to solve this thing and get that should be the optimal solution. Right. Well, so Hilbert's idea is that you should be able to rely on the curvy paths. They have well-defined energies, right, that you can evaluate, but they're not optimal. Okay. But why not use those to sort of, by the sort of topology of entrapment, use those to get sort of a measure of energy on the straight line path. Okay. And anyway, you have to be careful about how you do that because in some settings there'll be too many solutions. Okay, but anyway, what I want to talk about much later in the 30s, Sobolev, and then Schwartz. And I'm going to give credit to Schwartz, so I think almost everything I used was in Sobolev before, 10 years before Schwartz, and Schwartz did read Sobolev. But anyway, whatever. They have kind of a nice picture about how this transfer of this dependence between the energies that we can put on the curved path should relate to the energy we want to put on the straight. And this is a kind of explanation, sort of account you get in almost all elementary books on distributions. You know, when we attribute a strain energy, stored energy, to a region, think of it as that what we really know is that if we take a probe and look in that region, we'll get an answer, right? But different probes will give you different answers, but there's got to be a system in those answers, right? So if one probe gives you 2 times the value of another probe, it'll do that all the time, and so forth. Okay. This is a metaphor for test functions. But the justification is sort of this: we really aren't interested in what goes on at a point. Maybe that's somewhat meaningless. What we want to know is, if we look at a region, especially something like energy content, right, then let's think about it as kind of processed through some sort of probe. Okay, now, what this allows us to do is we take our broken line function at the top. These probes, what they do is they wind up smoothing the thing. And they do it in different ways, characteristic of a probe, right? But these things obey the regular calculus, right? Okay? And this is the setup of the relationship between the thing that doesn't straightforwardly have a meaningful energy, and it's a translation scheme that takes you to a whole family of guys that do have meaningful energies. Okay. And here's the trick, then. I hope this explains. Okay, we want our straight line solution to have a stored energy. Now, obey this equation, that is, the string equation. Well, I don't understand what you're asking for. You asked for a curvature. What's that? Well, I don't have it. Okay. Well, but you got a bunch of helpers around, little corporals. You're a general, and yeah. So you say, hey, which way do I go? Well, then they smooth things enough that they can follow the instruction about curvature, and then they say, go left or right. I don't hope that helps. Okay. But once you got this sort of apparatus in place of this sort of this space of test functions, right, taking your target functional and converting it to something that then will make sense about in terms of regular calculus ideas, then you can transfer back and actually set up the notion of a generalized solution that allows my sharp-cornered string to both have a local energy content at the curve, right, and in a generalized sense to obey the equation. But this is a dependence between a group of different sentences that are carrying different aspects of information needed to get this system to work. So the test functions and the result after smoothing, those are like the nephews that help out dad, uncle. And so I just said that. Okay, and I call this phenomena, I took this from my thesis advisor, they meant by something different by it. The distribution of linguistic labor. You know, the basic equation by itself can't really accommodate some of the demands on it about storing energy, but if it's got some helpers to spread those duties, then you can get the whole system to work. quite well. Okay, that's the gem. Now, so that's the one sort of idea. Now I want to go back to first sort of a narrow sort of conceptual problem that occurred within computation and explain how the functional analysis unraveled that in the 1960s. And then I'm going to suggest that those ideas are very helpful to understanding more basic things in mechanics generally. Okay. But I want to talk about finite elements, and as I understand it, I don't know as much about it as it started in the 1940s, I think, with British aircraft engineers that wanted to estimate the stresses in a complicated structure like an airplane. Okay. And so there's going to be two parts of the story. First, how they thought originally of what they were doing, and what the functional analysis, no, you're secretly doing something else. Okay. And this is a well-known expert on finite elements saying that the seeds of the theory, though it gets taught as functional analysis today, that's not where it started. Right? The seeds of this thinking were grown in an entirely different garden. Okay. And this is what he had in mind. Going way back in the 19th century, structural engineers figured out how to handle one-dimensional member bridges, that is, determined and underdetermined bridges, which have, rods and stringers and things like that, and could estimate the stress in one of those things quite well by pretty simple methods. The aircraft engineers said, well, why can't we do that in 2 dimensions, right? Why can't we just, if we have a complicated structure, let's just build it out of little 2-dimensional squares or something, or triangles. And they actually got pretty good results this way. They certainly weren't going to find analytic solutions for most of these cases. But it's crazy, in a sense. If you had real squares like that, right, and tried to hook them together, all sorts of horrible, anomalous stresses develop. Okay? So, especially if you take a little square and you shear it, have transverse stresses, you're going to get horrible problems in the corners. And even with perfectly normal stresses, the surroundings, if you have a cutout thing like that, you're going to get infinities in the corner. And they had some baloney about, okay. But that's the garden in which these ideas grew. Okay. Now it did take the functional analysis. They looked at this and they were quite surprised to find that these things were doing some things that actually guys like Karan had sort of suggested, but nobody had followed up. And once they figured out what was really going on here, they realized that was a funny, wrong picture, and that the finite elements were applicable to a whole bunch of situations, right? Almost, in fact, I'm going to generally talk about degree 2 models, right, where you get by with very simple elements. But almost, well, I'm mainly also going to be talking about elliptic settings, but modulo that, this is a pretty universal method, at least for getting some very good answers. Okay. What were they doing? Well, we need 2 basic ideas. The first of which is this Schwartz idea of conveying notions of like energy and so forth to things with broken lines that don't, extending calculus rules. The second thing is that they recognized is that without realizing it, that the principle of virtual work was almost always in the background of these problems. And virtual work is sort of a traditional way of really emphasizing energetic considerations, particularly in equilibrium situations. And what this means, if you got a bunch of kids on teeter-totters, right, and you want to know in what configuration or configurations will they remain stable, virtual work says if you wiggle the position of any of the kids, up or down in this case, Then if you're at equilibrium, there'll be the system itself, once it's wiggled, will have a response function that'll tend to pull it back to where things started. Whereas if you're not in equilibrium and you wiggle it, then it'll just get worse usually. Okay, so anyway, that's a very ancient principle. Bernoulli's formulated it first, but it was known to Euler and Descartes, and even goes back to medieval times in some forms. Okay. And I used, a finite system there with teeter-totters, but it would work for a continuous system, such as a string. So we have a manipulation on the string, and it's in equilibrium if the virtual work vanishes. The work you put in is going to be countered by the response. Okay. Now, in this drawing, which isn't that great, but notice that the manipulation, I sort of symbolize it by a line saying what you pushed on. And then below it, I have the system that's going to respond that has a shape, and it will change that shape under the manipulation. Conceptually, those are completely different things. As functions, though, they look quite a bit alike. Right? And that, in a lot of settings, particularly with the endpoints that we've got, allow us to put these representatives into a common space, and we have a Hilbert space. So we have the manipulation in a common arena with the response. Now, not only to this space, let's flesh it out by using the Schwartz type ideas and put in a bunch of curves that have sharp corners. In fact, in the simple case I'm going to look at, we just need to put in a bunch of these sharp cornered straight lines connected by nodes. Okay. And then, once you do this, you get this kind of picture that shows how general it is of what was actually those aircraft engineers were doing. They thought they were taking the little elements and seeing how they affected one another. But what they were really doing is that they had a Hilbert space, and inside the Hilbert space there was a subspace of these broken line guys. Okay. The true equilibrium configuration is the thing with lowest energy in the full Hilbert space, but what the calculations were what the minimum energy thing would be in the little subspace, right? So, and since I could usually prove that if you had enough little kinks in your finite element, you would get pretty close in your approximation to the desired solution. This is a really Ritz method. But the engineers didn't realize that when they devised it. Okay, and that's a surprise. What the surprise was is that they didn't see this conceptual difference between a manipulation and a target system, because they were blurred together. Okay. And go fast. Okay, so this is the beginning. I'm going to have more to say, but this is the beginning of the explanation of some of those anomalies that I worried about in basic setting up your differential equation technique. But in particular, remember I said that if you hook two plates together really, you get horrible things along their edges, right? And they sort of, but they weren't really putting anything together around edges. When you look at the finite elements and you understand the manipulation thing, you see that these are little hat functions, those are your basic finite elements. They're overlapping. And then you express how one region reacts to another through things. There's nothing about boundaries playing any role here at all. Those are just the hat functions for two dimensions that they were. Now actually, I should say, since I do talk loosely about beams, I'm really talking about a membrane. To do a beam, you need, it's a fourth degree thing, so you need little curving things. Now, Okay, so that was the explanation of what these finite element guys, why they had these successes, but with a wrong picture of what was supporting their reasoning. I mean, it's a beautiful little theory, this functional analysis thing, that one space is acting on another, but they are things of the same mathematical type, so you can put them in a common space. Okay. Now, I think, retrospectively, I mean, what I just said, however ineptly expressed, is just standard history. But I think if we go back and look at what Thompson and Tate were doing, or any of those great masters of classical mechanics in the 19th century, they were doing something very similar. That they were, in setting up a differential equation model, though it was supposed to be continuous and flexible or whatever, they really began by reasoning in a little finite element space to kind of guide them in setting up the model. And then they moved to a limit which gave them the regular differential equation. Okay? And you can do this, I mean, because there's a mimicry here. You know, you're trying to get really to a target model in the continuum, but because of this sort of copycat aspect of the finite elements, you can translate the steps you should be rationally need to take and do them on the finite elements. Then they sound, but then you get these little weirdnesses, you know, about that flexible things become rigid when you get small, stuff like that. And anyway, I read it. So, I mean, that's the reason why this mysterious postulate of rigidity that you get in Thompson and Tate, it's really a justification for being able to get a very simple finite element model of the interaction, or what happens under manipulation, right? But we're doing with a little finite system, so if you rigidify something, it's in effect turning it into a finite degree of degrees of freedom system. But you're not really pretending that flexible things are rigid at small scales, or the things that you're usually. But this is why it's actually important, or I think it's kind of an interesting lesson in history of science. Many Victorians, or people of the period, because they overlap like Boltzmann, explicitly argue for atoms and molecular structure on the grounds that when you set up the equations, you've got to be dealing with these little finite things, right? And little mechanisms. So this is actually for a Bernoulli Euler beam element, kind of dressed up. You got springs in it, yeah, and fibers and all that sort of stuff. And they thought, well, the equation works pretty well as a good model for a beam, and we set it up by appealing to little things that look like that. Probably their structures pretty much like that have to be in the beam. And Boltzmann, I tried to find it, but I couldn't find my book. It's quite explicit about arguments like that. There are more arguments like that in Boltzmann than you'd like to think. Right? But I say, what we've learned, this is falling victim to kind of what I'd call semantic mimicry. Right? The finite elements will always work if you have a nice continual model. This is no evidence of any underlying reality on a smaller scale. Or this is sort of a picture of what I just said. So you've got a beam up at the top. Here you get your classic model, but the kind of to get to that classic model, the Victorians built these little dressed up finite elements, glued them together, and then took a limit and went up to the beam element, when really it should have been viewed the other way around, but that they thought that that was foundational for the validity of okay, so that's, I mean, I have some more things to say. How am I'm okay on time? Yeah. This is at least one part of really, because you can make them very concrete and dressed up like this, it made, Kelvin's very explicit about this a lot, made them feel more secure that they were modeling things correctly, right? But what they were really, the functional role that these little dressed up models played was peaking at an approximation to the equations that they were. But that's good that they did that, but that's what I mean, that there is a hidden dependence there. Okay, and it is important to realize, I think, that you have people that, like Duhem, that are often regarded as very bad guys in his philosophy of science, except for people like von Frossen, whose views have nothing to do with the real Duhem. But he criticized, he says, I think that there's mimicry going on here. That, and Mach said something similar, but Duhem is much more on the money. And all developments in thermomechanics sense have gone to prove Duhem right, including what I've just gone through. Okay, now another second thing I'll try to, another aspect that I talked about to this whole problematic has to do with those restrictions on movement that the Victorians used. So remember, to get your string equation, you have to assume that for some mysterious reason, that when you pull a string, it will not shear to the left or right. It will come out straight and follow a straight path backwards. And that's, okay. And even worse, when you have things like plates and so forth, then there are all these basically versions of the same assumptions about that you can break them into little blocks and none of the blocks will shear. Okay. And so that's usually part of the story of, besides what I've also given about how they get to these equations again. Okay. Now, let's see if let me state what I'm after in case I have to go too fast. Right now, partially tracing back to Hilbert, there is a great worship of the idea that scientists propose theories that establishes internally their descriptive content, and again, you don't have to look at approximations and so forth. Now, that sort of notion of theory really can't be supported very ably in classical mechanics practice, and if you adhere to it without thinking, then I'm going to talk about a very famous and very great scientist who adhered to it without thinking, you get yourself addressing all sorts of pseudo problems that don't have any real physical basis to them. And Bob and I, there was a great functional analysis from Carnegie Mellon came over at one of Bob's conferences and says that Truesdell ruined continuum mechanics. And I'm going to explain what he meant. Okay. Now, Truesdell school, which traces back to Hilbert through Hamel and other people, did do great clarification work in continuum mechanics, vis-a-vis cleaning up what was important to it and what wasn't. And in particular, there are really difficult scaling problems that have to work together to make continuum mechanics work. Somehow philosophers are not aware of these conceptual difficulties. And particularly as it stems from the fact that there are two fundamental different kinds of forces involved in a continuum. The ones like gravitation where, so we got that point P, those are forces that come from far away in the material. Okay, so I symbolize it by a spring. That's like gravitation or electric attraction. Those are called body forces. But then there are also the neighboring material take any little surface, or almost any little surface in the material, there will be a way in which the stuff outside that surface pulls on the interior. And those are called traction forces, and they live on the boundary. Okay? Now, these guys, these two kinds of forces, are not dimensionally coherent. One guy is tied to area, the traction forces, and one guy is tied to points, or volumes, right? And if you just try to sum them by some sort of naive integration, all the traction guys are going to disappear, living on a, you know, an area of measure zero. Okay, so you have to be very careful about the shrinking in process, how you specify it, and that, if you do it correctly, for the traction forces, the result is you get a stress tensor, which is kind of a different animal, but that's the proper animal that has to interact with the body force density. Okay. And so the Truesdale school straightened out a lot of these basic scaling things that have to work, how they have to work, and they cleaned them up and got all this sort of stuff, assumptions about how strings can move, all those constraints I talked about. You have to clear those out to see the shrinking process in its pure form. It's sort of necessary for the coherence of the discipline. So that's Truesdale's great contribution. Okay, now I'm going to mention real quickly, I have another paper about this. Scaling to get to differential equations is very important. It's a very important part of mathematical analogy, but there's always something kind of inherently weird in this methodology. And in fact, I have a paper if anybody cares about it. Leibniz, who set up the first PDEs, or pseudo, or close to PDEs, worried about this explicitly, and many wild things in his philosophy seem to have been born directly from this tension. Namely, he knew that to get a differential equation, you're assuming that things behave the same as you get smaller and smaller and smaller, all the way to infinite size, and then your physics becomes simpler. Physics is simpler in the small. But he realized that he was plowing over behaviors that things stopped scaling. He knew about microscopes and stuff, and he had various. And in truth, if you take steel about 10 nanometers, you start seeing all this grain. And those grains don't behave like the steel. Okay? But to get the whole methodology to work, you have to scale all the way to size 0. What could be the justification for this? Okay, so this is another branch of weirdness that you are taught in elementary physics, but might trouble you if you care about rationality. Right? Why are we doing that? Well, I'm going to give a short answer. I can give you a longer answer. It isn't because we think that that describes lower scale reality. It's because we have to get to that differential equation because it's the doorway to inferential pathways to lead to bigger behavior, bigger scale behavior. So if you take an iron beam and you confine its two ends, then that induces vibratory modes that'll store energy. Just like in a vibrating string, you know, you get your energy stored in your fundamental and your active and all that. Okay. And that is a behavior at a higher scale level than what you're looking at when you start with your assumptions about iron. It also involves the confinement of the end condition. So it's a cooperation between end conditions and the interior modeling, giving these large scale things. Now the long and the short of it, the route to that is just a Fourier transform. To find the modes from the differential equation. Okay. If you discretize, and you guys know this, and take a broken line thing and apply a Fourier transform, you get a god-awful mess. Right? So you really have to theoretically smooth things out so that you get the right story that connects your modeling to the right larger scale behaviors you want to get. Okay. So if you throw out the differential equations, this artificial extension down to size 0, then you throw out most of the valuable results you want to get to from your differential equation. And in a sense, by artificially overscaling down to an infinitesimal level, it acts as a filter that removes some sort of small-scale noise and gives you kind of dominant behaviors asymptotically on a large scale. That's the way I look at it. Okay, getting back to Truesdell, that little digression was, his school did something really important in clearing up what the required methodological picture was. That's the good side. Now we want to talk about the pseudo-problems that sort of worship of a single formula gets you into. And there's been a revolt against this, but just the last 10, 15 years. This sort of focus, once they got rid of those constraints, then you have to put something in your differential equations that distinguishes a fluid from a bar of iron, from a block of chocolate, from every other material. And they were sort of forced by unity of meaning considerations. That has to appear at a so-called constitutive equation level, which is at the point, the sort of artificially point-based level. Okay. And then that creates a demand, and there's a wonderful old article by Stuart Antman again, when American Mathematical Monthly, way back. This gives you the task of taking something like as familiar as the string equation and find constitutive equations such that from them you can get back to the old string equation. Right? You can't use those old dodges that we used to do, right? And now, but this is finding something at a point level that'll give you this kind of behavior. And it ain't easy, right? But here's the thing, and this is what the functional analysts have just realized, and this very much ties in with the growth of multi-scale methods that Bob was talking about. When we actually know what makes strings behave the way they do, and it's way, way higher size scale, but still mesoscopic, strings are composed of fibers, polymer fibers. Right? And basically, because of the geometrical entanglement at much higher scale levels, strings have a natural thermodynamic state that they want to get to most probably, and that means when you stretch them, it's actually sort of an entropic force that restores them to their natural position, right? But this is, okay. You can have nice models of these sort of laminated structures having fibers like that, and then these are hard to prove, but it makes more sense that asymptotically these fibered structures will behave like strings. Because there's a big energy cost to being stretched and a particularly big energy cost to being sheared, so asymptotically it becomes, you suppress any ability to go to the left or right. But still, this model does not mean they do not resist bending, like a beam would. So anyway, this is the right way, right, okay, to get the kind of an explanation of why the string is a good model for a lot of natural systems. But it starts at the right scale level where the real explanation lives. It does not try to find some sort of projected down explanation at a point level, where any rule won't make any sense to you except as a projection of this natural things about fibers. And this answer, even if you found a constitutive equation that would get you the string behavior, what bearing it would have on reality is dubious. But this is actually the right answer. Right? This is grounded in the real world about why gives you a real answer about why those particular models work. And as I said, these are multi-scale models. Usually you start with a top scale model, and then you have a sub-model that locally sees if the conditions on a lower scale are consistent with the upper scale. Anyway, I won't go through that. But the long and the short of it is this combination of multi-scale work and this realization. We're asking a lot of pointless questions just because the Truesdale school had this idea of the meaning of an equation, and it left them no recourse except to put the constitutive equations down at an atomic level. But if we don't want, okay. So again, we have one of these. Maybe I'm going too quickly here. I mean, this is again another thing where you don't work with one model or just one representational structure. There's a consultation going on between scales in this kind of setting, and that's the right way to think of what the content of the string equation really is and what its source of descriptive validity is. So, let's see. Okay, so the string equation needs some help from other scales and from finite elements and all that sort of stuff. That's how we get a successful band to go. Okay. And I can't really prove this, but this is so ingrained in orthodox linguistic philosophy. I'm really basically a philosopher of language. It really comes from a naive idea about how a single sentence is supposed to carry all the descriptive content, right? But really, little pieces that are being carried, important pieces are being carried all over a whole bunch of different representational structures. At least that's the moral I get out of it. Okay, so worshiping the single formula, that's having this naive view about how they carry descriptive content, how a bunch of sentences collectively carry this. So they're just repeating a good modeling needs some help from its friends, including some peeking. Now, the last thing I'm going to say, this is again about Bill and a couple others here being more familiar with it. Actually, I was quite astounded. Bob has a couple of really able thesis students at Pittsburgh, Lee and Mike Miller, have been looking at how philosophers have been trying to deal with quantum field theory. And these philosophers, and their number is many, they're a very dominant school, say, we don't bother with Feynman intervals. We don't bother with renormalization because that stuff isn't rigorous. A philosopher needs to study a rigorous theory so that their results can be rigorous. As if anything philosophers do is timeless. I don't know. Anyway. And they trace this really back to Hilbert, who is one of these 20 problems, or however many there were, number 6, asked for an axiomatization of classical mechanics, and he meant continuum mechanics in the context of the time. Now things changed because quantum mechanics came along. But that was a great hope. It was a great hope that inspired all the logical empiricists, so that's one of the reasons we have this great emphasis on logical structure. I mean, many useful things came out of that kind of study. There was a reasonable hope at the time, but as I like to say, a funny thing happened on the way to the formalism. And it's basically quantum mechanics came along. I won't go into that here. There can't be a foundation of the sort Hilbert was expecting. And the real answer, what I was trying to sketch, the beginnings of an answer about why classical mechanics is astoundingly successful as a set of tools for modeling behavior, involves the fact that there are many different factors that counterbalance one another in shaping your view of what you should write down, how you should study it. including all the approximations, right? See, and multi-scale modeling, those things do not lend themselves easily to an axiomatic framework. Conclusion, so much the worse in this kind of setting for axiomatic frameworks. We want to understand why they work. Right. Okay. So, okay. So these guys that worship theories and rigorous theories, in the context, God help us, of quantum mechanics, I think is betraying some of the deepest obligations of philosophy to have an open mind and study directly how might you carry physical information usefully in a bunch of sentences. And there are many different models and ways that you could go. I've sort of sketched some of them here just based on history. Okay. And this is why you guys that know how to get the numbers, there's so much important data that I think necessary to holding together a body of knowledge that we as philosophers need to pay a lot more attention to. Okay, so sometimes the best way to get ahead in nature is not to be too fastidious about standalone rigor. That doesn't mean that this stuff can't be studied rigorously. Those functional analyses are a heck of a lot more rigorous and use trickier mathematics than any of the axiomatists. Right? But you do it in a more general framework that reflects the varieties of the ways that language can be useful.
Yes, Jim.
Just very quick question, I'm sure it's a simple answer. Why were some of those derivations, did you need finite elements as opposed to infinitesimals? I don't know the Leibniz derivation of the beam example.
Well,
I would imagine a priori that he reasoned with infinitesimals.
well, you know, there's two things about infinitesimals. You know, I'm sort of concentrating, but I would say there's a separate thing about the justification of infinitesimals in the calculus.
Yeah.
Which is one, but then there's a problem with justifying the physical infinitesimals.
That's...
Okay, and that is, look, a strain or a stress tensor is a weird thing. It is basically a point with sides to it.
Yeah.
You know, that you can pull on, but then there's a linear structure, so there's only 6 different, you know. Now that is a very weird conception. Okay, that's not particularly related to the calculus infinitesimals. Right. And so, but just from the very description I gave is point with some sides to it.
Yeah.
Right? And of course, then naturally to make sense of that, then you also have to get why you have a curvature. You have to start with a surface and then shrink down to this thing that still is like a little body with a geometry to it.
Yeah.
So it's that nexus of ideas that, so they didn't use finite elements, they would say element, okay? And they'd say, oh, it's going to be infinitesimal, but they didn't tell you what that was. But the reasoning drew upon very heavily, and Lord Kelvin would be very explicit about this, you relied upon your sense of finite, your experience with rigid body and spring constructions, maybe some dash pots and things. And you still see those as your elements. They're supposed to be infinitesimal, but it is what is the steering mechanism in those modeling assumptions, however you want to describe it as a finite element or an infinitesimal element. And what I am trying to do is explain why you could, there's actually a very basic problem with the continuum. If you take a string, you want to know how to set up the equation, well, look at a smaller thing. But strings are completely scaling. No matter how small, you get your same problem you started with. Nothing simplifies, right?
Yeah.
As you move it. But if you rigidify things, then you can turn an infinite degree of freedom problem into a finite degree of freedom. That was the transition that they had to make. And that's why, you know,
No, this is really interesting. I want to follow it up if I may. It's related. I sometimes work with a friend who's a mathematician who specializes in partial differential equations. And we talk a lot about continuum mechanics and stuff like that. And I cavalierly talk about waves, like sound waves. And he looks at me like a missionary talking to a cannibal. He says, waves in the atmosphere? What are you talking about? A wave is a solution to the wave equation. It has to be a continuum. And there are no air waves, there are no sound waves, there are no water waves. There are only waves in continuum. So he said, then all right. And then we batter back and forth. And he's got a very definite picture. And he's very much a working mathematician, applied mathematician. And but he definitely has a picture where he starts from the continuum and gets strings as approximations out of it. So he's working in almost exactly the opposite direction you are. Do you know what I mean?
well, I'm not sure, he's factoring things into one dimension.
Yeah, he'll take a one-dimensional or a wave in a solid. I mean, typically we talk about Hookean solids, modeling, something like the Earth or something like that. But those are waves through a continuum. And what goes on with an actual string or the actual Earth, he would say those are disturbances which have some similarities to a wave. Yeah. How do you sort of interpret that kind of behavior? I mean, he seems to me, I'm not defending him as opposed to you. I'm actually find myself slightly more sympathetic to you than to your friend. But it looks like he's coming from a highly idealized and getting the actual world as a later development out of it.
Well, I actually have related to this.
Yeah.
Another paper. There's some deep things going on. Okay, now words, especially like wave, are going to have all sorts of different natural homes.
Yes.
What he is emphasizing to be sympathetic to you, and this is actually, I'm writing something about that fight between Bob and Gordon a lot about. There is a need for a notion of wave such that Hadamard developed of a discontinuity surface, right, where the singularities travel. It is a very deep mathematical notion that you have to pay attention to. And often, even mathematicians, but certainly philosophers, slough over that. And so I think that there is this very important notion of a wavefront. Right? And and there have been a lot of realizations in differential equations, particularly in the 1950s and 1960s, that completely have made us rethink our notion of a solution to a differential equation. And that notion of wave that he is emphasizing, which becomes very sophisticated, is very crucial to understanding. So when the way I would understand it, he is holding to the ground. There's an important notion here that's really primary. Really primary is in somewhat the eye of the beholder. But in the right kind of beholder, he's right.
Okay, good, thanks.
So thank you very much for this wonderful lecture, and I'd like to make a couple of comments. First of all, is that after your lecture, I realized what a big mistake Euler perpetrated, because when he discovered what you now call the Euler-Lagrange equation, he did it by discretization. So he had this integral and divided it in elements, and it just reasoned one element at a time. And when he saw the proof of Lagrange by using textbooks, we do it now by integration by parts, he thought that it was nicer, that his elements were maybe a deus ex machina just to prove the thing. Because if that derivation that Euler had stayed in the literature, maybe people wouldn't have put so much emphasis on going right to the delta x going to 0 to derive everything. Right. So
look, it's very, without developing the orthodox calculus, how you could have built the Schwartz type story, you couldn't, you need those orthodox calculus.
Yeah, but I think in Euler's derivation of the Euler-Lagrange equation, there's a lot of merit in that he already uses these finite elements. And this disappeared because Euler thought that the approach of Lagrange was neater than his. And then another
I think you actually mentioned that these things are all over 40.
and another seen in your after your lecture, I realized this is very much connected to now this what we call maybe geometric integration and other similar approaches in solving differential equations. So in the old days, we were taught you have this continuous model, and then you discretize it, and this discretization is just something to get the numbers, and you should only take into account the differential equation, not the physics or the outside. And then it had become quite clear in the last maybe 25 years that when you are going to discretize the differential equation, you should first look at the origin of this differential equation, because some ways of getting numbers out of it are consistent with the broader picture of the physics or of the biology or what have you, and some are not consistent with the general principles of, so this is the whole business, say, we call this symplectic integrators, that we've got a reality that we assume that is based on Hamilton's principle, and then we have the equations of motions of Hamilton, but when we discretize it, it's not enough to look at Hamilton's canonical equations. We have to look at really Hamilton's principle, so to speak, to incorporate the physics into the discretization we use to get the numbers. So I think
buried in here is a simpler version of that, but related is that seeing virtual work as involved, and then you're using sort of crypto-integral equations here, really carrying physics, and so you can tolerate singularities inside the interval, so that you've got a story that tolerates shock waves from the interval. So that is a related sort of, look more at the physics that gets you there, even if, and even with Rob's things, virtual work is an early version of getting the notion of potential energy. So we were using sort of crypto-energetic considerations, were sort of playing a large role in steering this stuff in the right way. But the Hamilton things.
Okay, I'm sorry to cut things off. I hope you'll have a chance to discuss things with Mark further, but there are a few people who have flights to catch. So let's take a moment to thank Mark for a great talk. And we have listed closing ceremonies on the program. I'm not sure if Rob has.
Yeah, closing ceremonies are in my usual extensive style. Every professor speaks for a microcentury. That's a quote from Bill Fife. His corollary is, unfortunately, you can't get more than a million lectures out of any of them. My error is I never speak enough. So sorry about that. I want to say thank you very much to everybody who came. This conference has exceeded my expectations. The engagement between serious scholars on the philosophical side and serious scholars on the computational side has been excellent. I'd like to see that continue greatly. So there is a meeting in Pittsburgh in the fall at some point, where some of us might be going down to. I understand that. I don't know whether
it's October 2nd.
October 2nd or something like that. So already there may be opportunities for continuing conversations, and I hope that happens. In any case, we may have another meeting like this. That would be great. But I would like to thank everybody who helped out. We have lots of people who accrued the registration desk, and we had our chief organizer and speaker in the middle of the day, and the person who's going to be driving people to the airport is in charge of everything. And we have people help fund things. So I should thank the Rotman Institute greatly for its initial seed money. Actually, the bulk of the money came from the Rotman Institute. I also thank the Fields Institute for Research in Mathematical Sciences. I mostly want to thank everybody for coming and engaging. Well done, everybody.